So a problem, let's say a problem from chapter 32. Okay. Okay. Can I erase this now?
Yes.
Okay.
I can make this our last class.
First question.
Right, maybe out of here.
Write an expression, a mathematical expression for the magnetic field.
Oh God.
So write something like magnetic field equals, given this expression. So this is some electromagnetic wave that's traveling, and the electric field is given by this expression. First of all, in which direction is this electromagnetic wave traveling? Did we talk about this or no?
Yeah.
Sort of.
Last time? No? So in what direction is it traveling?
To the left, because it's got the same
Which
sign.
way is to the left? Your
The
left
negative-
is my right.
The negative x direction.
Negative who?
X. Or wait.
Negative x? Why x?
Well, I mean, the wave goes up and down on the z-axis, but it in total is
But
going
we
up.
wrote this one.
Why?
So in which direction is this wave traveling? That's not even over here. That's just, so you're supposed to look at it and say, it's traveling this way.
Why?
You're supposed to break the marker.
Oh.
The cap came off.
Should be
Oh.
So, come on, tell me. In which direction is the
y.
wave traveling? And don't say up, down, right, left, because I haven't said which way is x, y, and z.
Negative.
Unless, I mean,
The negative y.
in the negative y direction, that's correct. So, the y here tells me that it's traveling along the y-axis. So the y in that argument tells me that the wave is traveling along the y-axis. Now, how do I know if it's traveling in the positive y direction or in the negative y direction?
It has the same sign.
Then I look at the signs, right? This is a plus, and this is a plus. And when the signs are the same, in which direction does it travel?
Negative.
In the negative y direction. So the wave travels in the negative y direction. So the magnetic field is going to have some amplitude, but if that's a cosine, this is going to be a cosine. And the entire argument will be identical to that one. Identical. So it will be 1.99 times 10 to the 7th y plus 5.97 times 10 to the 15th t. So we need to figure out the amplitude of the magnetic field, and we need to figure out in which direction it's oscillating when the electric field is oscillating in the z direction. So how do we figure out the amplitude? What is the amplitude of this electric field? What's the amplitude of this electric field?
3.5.
The 300, whatever multiplies the sine or the cosine is going to be the maximum value. That's the electric field amplitude. That's E max. Not E naught, because it's not initial, it's E max. It's 375 volts per meter. What is the relationship between the electric field amplitude and the magnetic field amplitude? There's a relationship.
E max equals CD max.
Exactly. So E max equals the speed of light in vacuum or in the medium that this is traveling times B max. So since the amplitude of the magnetic field is 375 volts, and C in vacuum is 3 times 10 to the 8th meters per second, then B max, the magnetic field amplitude, is 375 divided by 3 times 10 to the 8th. And what do you get?
If it was going through something that wasn't a vacuum, would C be given?
Then that would be the speed of, like if this is in water, then
Yeah.
this would be the speed of light in water.
Okay, it would be.
Yeah, which is different. And you learn to calculate that. It's very simple in physics 1, in physics 285.
1.25 times 10 to the negative 6.
1.25
Yes, sir.
times 10 to the negative 6
Yes.
Teslas, right? So I would write over here 1.25 times 10 to the minus 6. And this would be in Teslas, right? Maybe I'll put a capital T for Tesla. I like to put it way outside too. And what about the direction of the electric field vector when of the magnetic field vector when the electric field vector points in the positive Z direction? So how about we do this? Let's say this is the x-axis, this is the y-axis. What will be the direction of the z-axis, into or out of the board? So if the electric field points, if the cosine is positive, right? The electric field points in the positive z direction, so the electric field will be pointing this way at that instant. The wave is traveling in which direction did we say the wave is traveling? The negative y direction. So the wave is actually going, the wave is traveling this way. In this picture, it travels downward. That means that the pointing vector has to point that way, in the direction that the wave travels. So what is the connection between the direction that the wave travels, which is the direction of the pointing vector, and the direction of the electric field, and the direction of the magnetic field? S, the pointing vector, is defined as E cross B over mu naught. Mu naught is just a number, right? So if this vector points in the minus y direction, and the electric field points in the positive z direction, what must be the direction of the magnetic field? So that K cross B gives me minus J.
Negative 1.
Has to be what?
Negative 1.
Negative I? Agree?
Or, yeah.
Or what did you say?
I said negative 1, but I.
Yeah, negative I hat. Is that right? Let's check. Suppose this is minus I hat. Well, let's do K cross I. How much is K cross I? Let's forget about the minus sign. K cross I is what? Yeah, you can do it also like this, right? Go clockwise, the answer is positive. But I said K cross I will be J. But with the minus sign, the answer will be minus J, which is this. So yes, the magnetic field will then be in the minus X direction. So that will be the answer.
If the given was z hat, wouldn't it be negative x hat?
No, yes, that's good. There's a reason why I did this. The reason why I did that is because that electric field vector generally is written like this. It's the amplitude, and then either sine or cosine, and let's say that would be ky plus omega t in this case, right? Right? This k is called the wave number. But there's a vector associated with k. There's a vector, which is k, right? This is called the wave vector. the magnitude of it is the wave number. And what do you call the unit vector in the direction that the wave, and k is a vector that points in the direction that the wave travels. So what do you call the unit vector in the direction that the wave travels? It's called k hat. But in this particular case, right, we don't want to say that this is k hat, because for us, k hat is in the negative z direction. So in other words, k hat in wave propagation is a unit vector in the direction of the wave vector, which is the direction that the wave is traveling, which is not necessarily in the minus z direction. So for these problems, it is better to use x hat, y hat, and z hat. Because if you use I hat, j hat, which is fine, but if you use k hat to mean z hat, remember that k hat has another meaning as well. And so then it may be confusing. So those of you who take a more advanced course in electromagnetics, like if you're an electrical engineering major, you'll take electromagnetics, and then you will talk about a wave vector, the magnitude of which is the wave number. But a unit vector in the direction of the wave vector is called k hat. But we learned k hat as a unit vector in the positive z direction. So to us, k hat already has another meaning. So oftentimes you might see, so it's just easier to call it z hat, like if you mean a unit vector in the positive z direction, rather than k hat, because then you don't, if I write k hat, it's like, does that mean in the direction the wave is traveling, or does that mean in the positive z direction? But yes, it's better to call this then, just to be consistent with that, minus x hat. But it would be the same as minus I hat. With I hat and j hat, there's no confusion. The problem is with that k hat. There's just, k hat is a unit vector in the direction of the pointing vector, which is the direction that the wave travels. But that's because that's if that represents a unit vector in the direction of the wave vector. But to us, k hat points in the positive z direction. So that's why I use that notation instead, so that it's not ambiguous.
So it wouldn't matter if we put x hat or I hat on the test.
X hat, I hat, there's
Same
no
thing.
confusion.
Okay.
J hat and Y hat, there's no confusion. But if you put K hat, then it's like,
Okay.
It might be like, what do you mean by K hat? Right? You mean the direction in which the wave travels, or do you mean the positive z direction? There are two meanings, and so then one has to specify. So just so that you don't have to specify it, so that it's clearer, you just write z hat.
And then
Okay, what's another question?
I was gonna ask one more thing. Why would you? Actually, oh wait, no, never mind. I was gonna say, why would you indicate like the direction it's going, but the E wave goes down the z-axis, but it's oscillating up and down the x.
So it's a transverse, electromagnetic waves in vacuum are transverse waves. So both the electric and the magnetic field are both perpendicular to the direction that the wave travels. In addition, they are perpendicular to one another. So for an electromagnetic wave traveling in vacuum, the electric field is perpendicular to the magnetic field, and they're both perpendicular also to the direction that the wave travels. So they're all mutually perpendicular. So in this case, the wave is going down, like I take my laser pointer and I go and I shoot a beam of light down, right? So the wave is going down. So what this is saying is that at the instant that as the wave goes down, at the instant that the electric field points this way, the magnetic field we said points in that picture, as the wave goes down, when the electric field points this way, the magnetic field has to point this way. So that E cross B is down. But then this is going to be oscillating and then going that way, and this one has to go the other way.
Oh.
So that this E cross this B is still down. So as the wave goes down, the electric field is going to be doing this. It's going to be oscillating like this, and the magnetic field is going to be oscillating like this. Right? So at this instant, I wrote, okay, let's say, suppose the cosine is positive, so the electric field will be pointing out of the board. So at that instant that the electric field points out of the board, at that instant the magnetic field has to point to the left, to your left, in the negative y direction, negative x direction.
Does it matter if it's cosine or sine?
Now, that has to do with how, at the instant that it was produced. But if you have light coming from the sun, another question is this, what is I can ask, what's the frequency of this wave? How about I ask a more interesting question, what is the intensity of the wave? So what is meant by intensity? So there's a formula for intensity. Can I show you? There's a list of formulas, and I'll give you a list of formulas anyway. You just pick one and plug it in. I'll plug numbers in. But I can relatively quickly figure it out. So the pointing vector is E cross B over mu naught, right? So how about we write this in the most general way? I'm going to do a little derivation here. So I can write the electric field as the electric field amplitude, which is E max, and I'm going to put the vector right above it, so that could be in the positive z-axis, positive y-axis, positive x-axis, negative x-axis, whatever, right? So I'll just call the electric field E, and how about I write cosine of kx minus omega t? Suppose I just write it like that. And then I have to cross that with the expression for the magnetic field, which is going to be B max, and I'll put the arrow above it, and it would have to have the same here. Sinusoidal functional dependence, suppose I make it like this. And then I have mu naught. So notice, S would be 1 over mu naught times the cosine squared of kx minus omega t. And then I have the cross product applies to the vectors, right? So then I write E max cross B max, the electric and magnetic field amplitudes, right? And what if I take the average value of this? So the average value of the pointing vector will be written like that. I'll use the bracket notation to mean average. And then this will be the 1 over mu naught cosine squared of kx minus omega t. I want the average value of that. How about I write it like this? And I want the average value of mu naught. Right? This is just a vector cross with this other vector. Now, what did I say about the directions of the electric and magnetic fields? They're perpendicular to one another, right? So I'll leave them like that. So the question is, what is the average value of a constant?
The constant?
The constant, right? If you take a test and you get 90%, and you take another test and you get 90%, and you take another test and you get 90%, and you take another test and you get 90%, what's the average value of 90, 90, 90, 90, 90, 90, 90? 90, the same thing. It's a constant. So this would be 1 over mu naught. Now, what is the average value of the cosine square of something? Can I erase this?
Yes.
What's the average value of the cosine square?
Is it like 1/2?
It's going to be 1/2, correct. So let me show you why that's the case. So the average value of the cosine square of any, of theta, I don't care what kx minus omega t is. What's the average value of the cosine square? This will be, it's 1 over the period. What is the period of the cosine function? Is 2 pi, right? And then I integrate from 0 to 2 pi. And then it's the function squared, d theta. So those of you who know the trig identities, help me out. This is what? 1 over 2 pi and this will be from 0 to 2 pi. I think this is 1/2, 1 minus sine of 2 theta?
Isn't it sine squared? Sine squared plus cosine squared equals 1, so wouldn't it be 1 minus sine squared?
What is it?
Isn't it sine squared?
No.
No?
No.
No.
It would be 1 plus cosine 2 theta.
With the cosine is a plus?
Yes, if it's sine, then it's a minus. But you need to change the sine 2 theta to cosine 2 theta, I believe.
Like this? We can always double check, but I don't want to take the time to do that.
Correct, yeah.
Okay, let's say that's it. Right?
It is it.
So how do you do this integral? This will be, the 2 comes outside, so this is 1/4 pi. And then you integrate 1 d theta. So you integrate d theta from 0 to 2 pi. Plus, and then 1/4 pi. And you integrate cosine of 2 theta d theta from 0 to 2 pi. And this will be what? How much is the integral of d theta?
Theta.
Theta. From 0 to 2 pi, this is going to give me 2 pi, right? So this will be 2 pi over 4 pi. Now, this baby over here will be 1/4 pi. And then the integral of the cosine of 2 theta is going to be 1/2 of the sine of 2 theta, evaluated from 0 to 2 pi. Now, what will be the sine of 4 pi? 0. And what will be the sine of 0? 0. So all of this drops out. And how much is then the answer? 1/2. Now, if you decided to write this as a sine function instead of a cosine, what would be different? Well, in that case, if you had a sine over here, like a sine square of theta, you would have a sine square of theta, you would have a minus, but it's still a cosine of 2 theta. So this would be a minus, and this would be a minus, but it doesn't matter because all of this is 0. So you still get a 1/2. So the average value of the sine square of theta is a 1/2. The average value of the cosine square of theta is a 1/2. So therefore, the average value of this cosine square is 1/2. And then you have the average value of E max cross. Well, that's just a constant, so I'll just write it like this. Now, let's do this cross product. Right? So what is this cross product? Remember that I said that both the electric and the magnetic fields of an electromagnetic wave are perpendicular to one another. So what is the cross product of 2 vectors that are perpendicular to one another? What will be the magnitude of that? Suppose I ask, what is the magnitude of this cross product? It would be the magnitude of the electric field, of this electric field, times the magnitude of the magnetic field, times the sine of the angle between them, which is the sine of 90 degrees. And the sine of 90 degrees is 1. This is just the magnitude of the electric field vector. And this is the magnitude of the magnetic field vector times 1. So the magnitude of this cross product is this. So therefore, what is the magnitude of the pointing vector? What is the magnitude of the average of the pointing vector? It would be, well, this is a constant. This would be 1/2 mu naught times the magnitude of this cross product. But this guy here is just this. So this will be And if you want to, and this is the definition of the intensity. The intensity of a wave is the magnitude of the average value of the pointing vector. So take the pointing vector, take the average of it, and that'll be some vector in some direction with some magnitude. So it's the magnitude of that vector. That's the intensity. It is the intensity is the magnitude of the average value of the pointing vector. That's defined as the intensity. And because Bmax, and so this is one formula. You can use that to answer this question, right? What would that intensity be? It would be 1 over 2 mu naught, which is 4 pi times 10 to the minus 7. And then you multiply by the electric field amplitude, which is, the electric field amplitude is 375. And then you multiply by the magnetic field amplitude, which is this, 1.25 times 10 to the minus 6. And this is going to be in joules per second per meter squared. That's what an intensity is. And this intensity doesn't mean current. This I doesn't mean current. This is intensity, not current.
What does S stand for?
Pointing vector. It's a vector. It's this. S is this is the definition of S. It's a vector. It's a vector that points. It is a vector that points in the direction that the wave travels, right? And it has units of intensity. But it is not the same thing as intensity. To figure out the intensity, you need to take first the average value of that vector, and that'll be, well, like all vectors, it'll have a magnitude and direction. The magnitude of it is the intensity. Yes?
Can you do the right hand rule for the S and E?
Yeah, so, you know, S has to be perpendicular to both the electric field and the magnetic field. So 4 fingers in the direction of the electric field, palm in the direction of the magnetic field, S will be the direction of your thumb, of your right hand. So in this picture, I think I erased it already. We said the electric field is in the positive Z direction. We have it like this. So the electric field was this way. And I said that the magnetic field has to be this way, right? In the negative X direction. What will be the direction of this cross product of E cross B? Down. That's the direction of the pointing vector, which is right in the negative Y direction. So you get, I don't know what you get over here, but you know, it looks like you get a 10. That's like another 10. So 10. That's another 10. That's like 100. You know, something like the hundreds or so. Did anyone get a number by any chance? Just 186.
0.5.
186? Thank you. Or this is watts per meter squared. So what does this mean? It means that if this electromagnetic wave is traveling and it's coming it's coming from there and it's going through this door, well, roughly this is 1 meter and this is 1 meter. So, you know, half of this door is like an area of 1 meter squared. So that means that as the electromagnetic wave goes through that door, filling that door, 196 joules of energy will go through that door in 1 second. Well, not through that door, through half the door, because the area is 1 meter squared. So that you would get, if I ask what is if the total area of that door is 2 meters squared, what will be the total energy going through it in 1 second? Well, this is how much goes through 1 meter squared, which is half the door. Well, through the whole door, it would be this times 2. Right? There will be what, 372 joules in 1 second. And what if I ask you what's the total energy going through that door in 5 seconds? So this is how much is going through per meter squared per second. So if the area is 2 meters squared, then twice this will be how much energy is going through in 1 second. But if I ask 5 seconds, then you have to multiply this by 5 as well. So, just understand what this number means. What if I ask you what's the frequency of this wave? In hertz. What's the frequency? Well, omega is 2 pi f. What's omega? Can you read off the value of omega from here or there?
5.97 times.
It's the multiple of t. That's right. So that would be 5.97 times 10 to the 15th. That equals 2 pi f. So the frequency will be 5.97 times 10 to the 15th divided by 2 pi, and whatever you get, that'll be in hertz. What's the period of oscillation of that electric field? The electric field is oscillating, the magnetic field is oscillating. What's the period of oscillation of those electromagnetic fields?
Isn't it just the inverse of the frequency?
Let's say the electric field. So that period will be 1 over the frequency. So it would be 2 pi over 5.97, whatever that is, times 10 to the 15. And that'll be in seconds. What's the wavelength? Of that electromagnetic wave? Well, we have that the wave number is 2 pi over lambda. But what is the wave number? This one multiplies the space variable. It's 1.99 times 10 to the 6. No, times 10 to the 7, sorry. So therefore, the wavelength would be 2 pi over 1.99 times 10 to the 7th meters. Is there another way to get the wavelength? Any idea? How else can I find out what the wavelength is? Or let me ask you this question. How fast is this wave traveling? We said that it is traveling in the negative y direction. How fast? What's the speed of the wave? The E. What is the speed of the wave?
Would it be omega over k?
Exactly. Omega over k. That's the easiest way. So it's this omega divided by this k. So that would be 5.97 times 10 to the 15th divided by 1.99 times 10 to the 7th. And if this is 3 times 10 to the 8th, or very, very close to 3 times 10 to the 8th, then this wave is traveling in vacuum. And I don't know what that comes out to be, but that would be in meters per second. What do you get if you I mean, that would be how much is, it would be 5.97 divided by 1.99, and then 10 to the 15th divided by 10 to the 7th, that will be 10 to the 8th, right? So how much is 5.97 divided by 1.99?
3 times.
That's like 6 divided by 2. It's like 3. Right? Let's make it 3. So it's traveling in vacuum. Is there another way that I could have found the wavelength if I know the speed and the frequency?
Lambda times frequency.
Right. So the speed of the wave is lambda times the frequency. So the speed is this. If this is 3 times 10 to the 8 meters per second, and the frequency we found it over here to be this, we can figure out the wavelength. I mean, that would be 5.97 times 10 to the 7th, was it? No, 15. So that's another way of getting the same value of the wavelength. So that would be 2 pi. I mean, did this come out is 5.97 divided by 1.993? Or maybe 2.99 is what it's going to come out to be.
That's exactly right.
Okay, good. So then this would be 2 pi times 3 times 10 to the 8th divided by 5.97 times 10 to the 15, right? Actually, that's the same as this, right? Can you see how I went in circles? Well, when you do the 3 times 10 to the 8th divided by that, that will be 2 pi, and then this divided by that. It's 1.99 times 10 to the 7th. Same answer. Meters. But the most important, I'm not going to ask you 10 questions in this problem. I'll probably ask you 2 or 3 questions, and that's it. So, what if I give you the magnetic field? Could you be able to write down an expression for the electric field? Right? So, you need to know, I mean, I'll write this somewhere, right? So, if you know, from looking at the variable here and the signs, you can figure out in which direction it's traveling. That will be the direction of S, the pointing vector S. So that will give you this. This expression itself is going to give you, if I give you the electric field, then you'll know this, and you can figure this out. Or you'll know this, and you can figure the other one out. So you need to know the cross product. Now, how much is there to grade over here? If you mess up in the direction of the, like if you write down an expression for the magnetic field, for example, and you know, maybe you do this correctly, but you mess this up, maybe you're gonna lose points, right? What else is there to grade besides using this formula, which will be given, right? E max equals CB max. Right, so with that, you're gonna get the amplitude of whatever it is that you're calculating, the electric field or the magnetic field, depending on what I give you. But then this is all the same. Question is this, right? And that's gonna come from this. So do the cross product very carefully if you're not very, you know, if you don't have a lot of practice with it. But if you mess up, if that question is worth 5 points, and you write down the correct magnetic field or electric field amplitude, then I'll probably make that 2 points, and for the direction I'll make it 3 points, right? Cross product is more, there's more to it than just plugging in numbers into a formula like this. So you don't want to be losing points over, you know, a cross product thing that you do that, you need that for chapter 27, right? I said that I was gonna put a problem having to do with the torque on a loop, right? So mu cross B, so you have to know about the cross product. Okay, I hope you have fun on Monday, May 23rd, 2000.